Hey everyone! Have you ever wanted to design your own custom hardware and have it talk to a processor? Today we're going to do exactly that. We'll be creating a simple 32-bit adder in Verilog and then building a bridge to connect it to an ARM processor on a Zynq UltraScale MPSoC using an AXI4 Lite interface. This walkthrough will cover the following key stages. Project setup. Initializing a new project in Vivado, selecting the appropriate target device, and creating a block design. Verilog Module creation. Defining and implementing a 32-bit half adder in Verilog. AXI4 Peripheral Packaging. Creating a new AXI4 peripheral to act as an interface between the processing system and the Verilog module. This involves configuring the AXI4 interface, adding the half adder logic, and defining the register map for communication. System integration. Adding the Zynq UltraScale MPSoC IP and the custom AXI4 half adder to a block diagram and automating the connections. Hardware implementation. Synthesizing the design, assigning output pins to physical LEDs on the board, and generating the bit stream. And hardware handoff, exporting the final hardware design as an XSA file, which encapsulates the bitstream and metadata for use in software development tools like Linux. By following along, you will learn how to take a custom Verilog module and make it accessible as a memory mapped peripheral to the main processing system. So let's move on to Vivado. As you can see, I'm using Vivado 2025.1. Make sure that when you install Vivado, you activate the drivers for the Zynq MPSoC chipset. We'll start by creating a project. Hit Next. In this occasion, we'll name our project codesign_Vivado. I'm using the Vivado suffix because we'll also be working with other tools, and this way it will be easier to distinguish which software we're using at each point. Then we'll just select the RTL project and without specifying sources at this time because we're starting from scratch. When we see this list of parts, we can filter them for our own chipset. So let's go for the XCZU3 EG-SFVC 784-2-E. This is the fastest way to get there. So this is the chipset that's contained in our AUP ZU3 board. So at this point, let's hit Next. And we can see the summary. You can double check it here. And let's click Finish. Once Vivado finishes creating the project, let's create a block design. We'll name it codesign_Vivado_BD for block design. Next, we'll create a Verilog file by opening the Sources tab and clicking the plus icon to add or create design sources. Here we're going to click Create File. We'll select Verilog and call it half_adder.v. Then we'll click Finish, and at this point we'll add or insert the inputs, operands A and B, and the result, which is the sum. Since they're all buses, that is more than one bit, we'll activate the bus box and set sum as an output. Then we're going to set the most significant bit as 31 and so on for the remaining ports. As you can see, each of these ports is 32 bits wide. So let's open this Verilog file by opening or expanding the design sources and double clicking on half adder. As you can see, we have the 3 ports we just created here with the 32-bit buses. And since this is a simple sum, we'll just add this instruction: assign sum equals A plus B, and semicolon. The purpose of this video series is not to delve into Verilog, but actually demonstrate how a Verilog defined hardware element or component can be integrated into a system. So for further details on this topic, there's plenty of resources online. So the output of this 32-bit half adder will then be used to turn on a set of LEDs on the board, and as a return value to the program we'll develop in subsequent videos. As you can see here, the sum, which is our output, has 32 bits, but our AUP ZU3 board has 8 LEDs. So we'll be lighting up these 8 and ignoring the remaining subset. Let's return to the block designer. We'll add the Zynq UltraScale MPSoC IP by clicking the plus icon and searching for MPSoC. Then we double click the Zynq UltraScale Plus component. At this point, we'll go to my GitHub repository called CodeDesign, and you can find it at github.com/vicdini/codedesign. And here you'll go to the folder named Useful Files. In it, among other things, you will find a file called preset.tickle. So let's download the raw file and drag it to the desktop. So let's cut it from the desktop. So from here we can cut the file and paste it in the codedesign_vivado sources 1 new, and then paste it here. And now from our Vivado IP customizer for this MPSoC, we can go to presets, apply configuration, which will basically load this preset. Remember, it's in the codedesign Vivado and sources 1 new folder where we just pasted it. Let's wait a few seconds. Once it finishes loading, you'll see a set of check marks in the devices that have been activated. Now let's just click OK. Let's save. And at this point, let's go to Tools, Create and Package New IP. The top menu, the next, create a new AXI4 peripheral, and here we can define our AXI4 metadata. So let's just call it AXI4_half adder, and for its description, let's call it AXI4 half adder. Here we'll just, for completeness, add a name half_adder and use the Lite interface type, because it will be more than enough for what we plan to do. Do notice that although we're using 2 input operands and 1 output result, This would be 3 registers, but we're gonna leave 4 here in this box because the minimum is 4, and hit next. At this point, let's just leave add IP to the repository selected and click finish. Let's refresh the IP catalog. It's going to say that we need to close our block diagram. So let's close our block design. Let's close it. Okay. And refresh the IP catalog again. There shouldn't be much to do at this point with the IP. So now we go to Window, IP catalog, expand the AXI peripheral here, you can see. And right click on our peripheral we just created and click edit an IP packager. This will create a temporary project. Let's just leave the default settings and click OK. And as you can see, there are basically 2 files, AXI4 half adder, and if you expand this, AXI4 half adder Lite inst, which means for instance, over here inst. Let's start by adding our half adder to the sources, as these 2 files were automatically generated but don't actually have the logic we need. So we'll just click add sources, add or create design sources, add files, and then here we are in the new folder, half adder, and click finish. Here it has been added, and you can just double check. It has the same source code we created before. At this point, we double click this AXI4 half adder file. So let's scroll down to the comment users to add ports here, and let's write output wire. Then within brackets, we'll take the data width, subtract 1, and then extend it to 0. This defines the sum bus output wire. Now let's add a couple of lines for operands A and B. Next we go to line 45, which in this case is right above the comment instantiation of AXI bus interface, and right after the semicolon we're gonna write wire, then brackets, take again the width. This is basically saying from 31 to 0, A, and let's do the same for B. So now let's scroll down to the comment add user logic here and start typing half adder instance, then dot A, and a semicolon. This way we're mapping these inputs and output ports or wires to the operands of the result. And let's also scroll a bit up. Let's add the operands again. Now let's open the AXI half adder instantiation file. So let's start by inserting the ports. So we go to the comment users to add ports here and start typing output register, and between brackets take the AXI data width -1 to 0, call it A, do the same for B, and the same for sum. In this case, you might be wondering why we're calling A and B output registers while sum is the input wire. Well, we're actually looking at it from the perspective of the processing system. So the processing system outputs operands A and B to the programmable logic, or the FPGA side of the chip, while it receives as an input the result of the operation performed in the FPGA. So it returns, or it receives, a sum. Since we're going to be using just 2 output registers, we're going to comment the declaration of the default ones. For this purpose, we scroll down until we see the number of the comment number of slave registers 4. We're going to comment the first 2 because we're going to rename them. And basically, we're going to search and replace for them. Let's go to the next and call it A. And next, A. And that's it. We're going to do the same with B, or slave register 1, call it B. And for slave register 2 and 3, we're just going to go to the last line and replace slave register 2 with sum and slave register 3 with 0. So basically the last line reads A, B, sum, and 0. Those are our 4 operands, or 4 register values. Now, having defined the Verilog files, we'll continue with the package settings. So after saving, let's just return to our package IP, packaging steps. And here you can define your metadata as you prefer. Then for our compatibility tab, let's go to production lifecycle. You can go through these. And as you can see, important interfaces, remember we exposed the sum port because we're going to be using it by the LEDs on the board. So we can see this message up here, merge changes from ports and interfaces wizard. So let's just click on it. Wait a second, and you can see that the sum port appeared here in the output direction. And you can also see the size in bits. At this point, let's go to addressing in memory. We can see the customization GUI. And here it's important that you can see the sum port. At this point, let's just click repackage IP. And let's close the project, the temporary project. At this point, we can close the IP catalog and double click on Code Design Vivado Block Design. Here, let's just add our AXI4 adder. Pattern here we can see, and you can see this green bar that says Run Connection Automation. Let's just click on that, and this window we can just leave the default settings and click OK. Wait a second. Then to tidy up the diagram, we can just click this refresh or regenerate button. We can see that the half adder has been added here at the top right, and an important aspect is that we can see the sum output port here. To avoid issues with the operating system later on our board, we're going to add a constant value for DCM locked. So we can do that by clicking add IP and then constant and connecting it to DCM locked. Now we can regenerate the layout, and if we double click on the constant, it automatically takes the 1 value. In this case, that's the value we desire, so we'll just leave it at that with a constant width of 1 and a constant value of 1. The diagram should look like this. You can save. Now we're going to create a file that's going to tell Vivado to ignore unassigned pins. Remember, we created 32-bit buses and we're outputting the sum bits, and they're 32, but the board only has 8 LEDs. So there's going to be a subset that won't be considered, and if we don't do this, if we don't add this file, Vivado will throw several warnings or even errors. So let's go into the project folder. Now go into co-design Vivado sources, sources 1, then new, and create a new text document called unassigned_pins.tcl. And let's go into edit mode. Here we're going to insert this line, set_property severity and curly braces warning, then brackets get_drc_checks ucio-1 close bracket. That's it. Let's just save that. And let's return to our Vivado project and go to settings in the project manager. Then bitstream, and here we can see we have the TCL file, the pre file. You can click on these 3 dots here and select a new script. As you can see, it's within the new folder. You just double click on unassigned pins, hit OK, OK again. So let's run the synthesis. We'll wait a few minutes. We'll click Open Synthesis Design and hit OK. As you can see, we have 3 ports, or 3 groups of ports, A, B, and some. So for these 3 port groups, we'll just set them to LV CMOS 18 or low voltage CMOS 18. And we're going to focus on the first or lowest 8 bits of the sum. To find out which are these package pins, we're going to the AUP-ZU3 board, descriptions. We can go to resources, reference manual, open it. In the last page, the Appendix A PO pinout table, we can see the LEDs, which are actually LV CMOS 12, not 18, so we can change these. CMOS 12, all of these. And then again, we go to the lowest bits, start with 7, and we can say it's AF2. can either search for it scrolling down, or you can just type it in. So we got AG1 and so on. So now we save, hit OK, and at this point we get the constraints file. So we'll just call it constraints. Again, the TCL file we created a few minutes ago basically helps us tell Vivado to ignore these pins that haven't been assigned. Let's just collapse this item, run the implementation, click yes, save. Now we'll generate the bit stream. And at this point we just click cancel. If you go to file, export hardware, you're gonna get this message that it can't write the hardware definition as there are no generated IPI blocks. So let's click OK. Let's click co-design Vivado block design, right click it, create HDL wrapper, let Vivado manage wrapper and auto update, and click OK. And in fact, we get this message at the top right that says the synthesis and implementation are out of date. So we basically have to rerun that, and we can just go through generate stream. And this will automatically run the synthesis and implementation. So now that our bit stream has been finally generated, we can go to export hardware, and this time you see the form appears. We click on include bitstream binary, and we evidently include the bitstream as this is going to be loaded onto the FPGA. And let's hit next. We can leave the default settings, hit next, and finish. With a tool such as 7-zip, we're going to go into the root of our project directory, and we can see this XSA file. So if we right click on it and open it with 7-zip, we're going to see that it contains a set of files. To fix a glitch or a small bug, we can go to drivers. This is the component we created. Then source, and we right click on the make file and hit edit. Here we can see that this $ and this $ are misplaced in comparison to this one. Basically, we just need to add a $ here and delete this one. And similarly on this other line, then we save it, close it, and update the archive. We can see that the modified time is different. This concludes our work on the programmable logic with Vivado. Again, feel free to reach out to me on LinkedIn. I'll see you in the next video.